All right, let me go ahead and start sharing the agenda so you can see the plan here today. And because it's a little bit different than what I had originally planned, we've got sort of two agendas, but we're going to start with what I originally had planned because it's got a couple good reminders on here for you. So first, the elevator ride activities that we've talked about before are due on Wednesday, tomorrow night. And so I want to make sure that we have a brief conversation about those so that you're really clear on what needs to be done for those. And I'll be giving you time at the end of the day today to work on that. So the first one is feelings in an elevator, and it is a little mini lab type of activity. You can barely call it a lab since it's more of just an activity, but if you were in class that one day that B-Day was able to be there, then you have the chance to use the weights and the spring scale and sort of visualize it using that. For most of you, you're going to need to use the alternate method to visualize it, and that is taking a rubber band and attaching something to the rubber band, and then doing the same thing the students did in class, but with a rubber band and an object instead of a spring scale and an object. It's the same result and the same visualization, but just stretching up or lifting up as the elevator, simulating an elevator rising, and then dropping down, simulating an elevator descending, and seeing when does that rubber band stretch, when does it relax, and when does it just stay at a constant value or constant stretched length. And so you can really see the same thing whether you're in whether you were in class and use the spring scale or whether you just use a rubber band with an object attached to it. And it's more just to help you visualize. You're not obviously collecting any data, you're just visualizing something there. So use that activity with a rubber band for those that weren't able to come to campus to complete that and answer the questions. And it's more of a completion grade. It's really just getting started with getting you thinking about elevators, getting you think about your personal experience when you've ridden in an elevator, and then also starting to kind of visualize with a very simple activity what's happening there. Now, on the second activity, the elevator video analysis, that is the one that I think is a little bit more, I think, critical and deeper to make sure you're really understanding what's happening. And so we are going to take just a couple minutes and review a few things before we go on to the next part of the lesson on Hooke's law. So remember that these assignments need to be turned in on Axis, and we can already see that we will be on and off campus at different points throughout the semester. So it's just easiest to have one method of turning assignments in, so we'll stick with Axis. And make sure that as you're turning them in, that you are turning them in as single files and preferably in PDF format. And so the feelings in an elevator would be one file in one assignment. It's actually a lab category assignment. And the elevator video analysis would be a second assignment that goes into the homework category. But the feelings in an elevator is a 2-page document front and back. So scan that and put that in as one document for the feelings in an elevator assignment. And the elevator video analysis is a 3-page document. So scan that as a single document and put that in for that assignment. Any questions about those details of how to turn in the assignments, when to turn in the assignments? They're due tomorrow night before midnight Pacific time. Any questions from you on that information before we review a couple key terms that might help you with these assignments? All right. So I want to be sure that you remember a few things from first semester, and just make sure that these details don't get missed. So what is a force? Oh, I think my speaker, I think somebody unmuted there, it looked like, but my speaker must not be working right because I didn't hear anything.
Maybe like the energy of movement or something.
Okay. So I wouldn't use the word energy, but it does have to do with movement because force is going to change the movement of an object. What else do we know about forces?
Force is a push or pull upon object resulting in change of status of movement.
Good. So it's a push or a pull. It's going to change the movement. If it was at rest, it might start moving. If it was moving, it might change its movement or come to rest. So there's going to be some sort of change caused by a push or a pull. Anything else you can think of about forces?
It's between two things or objects.
Yeah, good. That's an important thing to remember. There have to be two objects in order for a force to exist. Were you going to say something different, Nico?
No, that was the exact definition I had on my notes.
Okay, good. Anything else you can think of? We've done a pretty good job of summarizing it. Was there anything else anyone wants to add? All right. Now, Lucia mentioned the term energy, and the only reason I would hesitate to use that is because I know what's coming later in this semester. We're actually going to define energy, and we're going to talk about how it takes energy to create a force, but it's a slightly different meaning. And so we will actually be learning about what is energy and how does that connect to forces. So that's a future topic we'll talk about. So what's a Newton in terms of physics and forces?
Newton is standard unit of force. It's equal to acceleration. It's
Can you say
equal
that?
to the Newton is equal to 1 kilogram mass accelerating at 1 meter per second.
Good. So it's the Newton is the unit we use for force, just like we use meter for displacement, we use seconds for time, we use newtons for force. And a Newton breaks down to a kilogram meter per second squared, or a kilogram meter per second per second. And that is because of Newton's second law. So when we think about Newton as a unit, that's what it is. But we also learned 3 Newton's laws. So someone refresh our memory, what is the first Newton's law referring to?
I don't know if this is the first one, but an object in motion will stay in motion unless acted upon by a force.
Good. So that is the first Newton's law. It's the sometimes referred to as the law of inertia, that if an object's in motion, it'll continue to move at that same speed and in that same direction unless there's an unbalanced force that acts upon it. You could also say an object at rest would do the same thing, stay at rest, unless an unbalanced force acts upon it. How about Newton's second law?
Is that the one that like F equals ma?
Yeah, so there's a nice equation that helps summarize Newton's second law. Basically, we're saying that the acceleration of an object is directly proportional to the force. So the greater the force, the greater the acceleration, but it's inversely proportional to the mass. So the greater the mass, the less it would accelerate with a constant force. And so that's just F equals ma in terms of a formula. Good. How about Newton's third law?
When 2 objects interact, the force on both of them is equal.
Good. So like Hannah said earlier, to have a force, there have to be 2 objects. And Nico was thinking the same thing. And the force that those 2 objects exert on each other is equal and opposite. So if A is exerting a force on B, B exerts the same amount of force, but in the opposite direction. And that is Newton's third law. Good. So just a couple things to review and help you kind of make sure you're remembering the terms, remembering the units, remembering the definitions to help you complete these 2 elevator exercises. All right, now what is F sub G? What do we mean by F sub G?
gravitational force.
Good. What's a synonym we often use for that gravitational force?
-10.
Say that again.
-10.
Okay, so that's the value we can use is
All right.
-10 or -9.8. But there's another word we could substitute.
Wait.
Wait.
Yeah, good. Weight. So in the first feelings in the elevator exercise on the back page, it asks you to figure out the weight of the 50-gram object. And so a couple things you need to think about. How do we calculate FG? How do we calculate the weight?
You use the
Kilogram.
acceleration of gravity and the mass of the object in F equals ma.
Good. So we're thinking about F equals ma, where m is just the mass of the object, and a in this case would be the acceleration due to gravity, which, like Bob said, 9.8 or 10 meters per second squared. So for that question, you need to take the mass times the acceleration. But like we also reviewed a few minutes ago, Newton is a kilogram meter per second squared. So on that worksheet, on that feelings in an elevator worksheet, when you're calculating FG, you can't just take 50 grams times 9.8 or 10. You have to convert grams to kilograms. How many grams are in a kilogram?
$1,000?
1,000. Good. So you're going to need to divide the 50 grams by 1,000 before you multiply by G, right? Because you got to convert it to kilograms, then multiply by the value for G to get FG. So a quick reminder, like I said, I wanted to go through all these units, all these terms, make sure you're remembering these little details so that you can complete that exercise correctly. Now on the second exercise, the elevator video analysis, you're having to draw a lot of free body diagrams. So what do you remember, Josiah, would just tell me one thing you remember about free body diagrams.
If like an object is on the ground, there's always two forces acting in opposite ways, like the normal force and then the weight force.
Good. So we're thinking about the forces acting on an object. And so like you said, if we're just talking about an object sitting on the ground, it would just be its weight due to the gravity of the earth and the normal force of the earth or the ground lifting it up. Hannah, what's something else you remember about free body diagrams?
I don't really know how to like describe them. Like you draw the object as like a little dot because you don't want it to be too complicated. And then you just draw the forces that are affecting it and like the amount of newtons that's pushing it or pulling it.
Yeah, perfect. You did it. You described it well. We start with the dot. The dot just represents the object. And then we label the forces acting on that object. And so, like we mentioned earlier, for a force to exist, there has to be two objects. But when we draw a free body diagram, we're focusing all of our attention on just one of those objects. And we represent it as just a dot. We simplify it down. How do we draw those forces? So she said we label them and we represent them. How do we draw them? What do they look like?
They're just like arrows or lines.
Yeah, just arrows. And what's unique about the arrows? What are some rules we have to follow or some guidelines we have to think about in the way we draw those arrows?
Well,
A
if you're
length and direction.
Say it again, Nico.
The length and direction.
Expand on that a little bit.
Like you have to make sure that if an object is just like standing on a surface and he has no acceleration, you have to show that the gravitational force and the normal force are equal. You also have to make sure they're in opposite directions because he's not moving left, right, up or down.
Yeah, good. So the arrow directions tell us the direction of the forces and the length tells us the value. So if they're balanced, like the example Nico gave, then the length should be equal. Now, I'm not going to require that you get out a ruler and get it down to the millimeter that you've literally drawn them exactly equal. But if you want them to look equal, make them look close or put congruency markers on them if you want to. We've done that before. And if you want to make sure that they're not equal, then just make it clear. You don't have to get out a ruler and scale it, but make one clearly shorter than the other or one clearly longer than the other. It doesn't have to be perfectly to scale. It just should be visually apparent which one is larger than the other. Okay, good. Where do all the arrows have to originate on the diagram? Where do they all start?
On the dot representing the object or thing.
Good. They all start on the dot and point outwards from the dot, right? So you don't ever have the forces pointing to the dot. They're always starting from the dot and pointing outwards. Good. So as you do the elevator video analysis one, quick review, just thinking this through. Really what we're doing is in the directions it says draw the free body diagram for the person on the elevator. Well, how many forces are there acting on the person?
Two.
Two. What are those forces, Greer?
It's like the weight and the normal force.
Yeah, exactly. So we just talked about the weight a little bit ago, FG, right? Would the person's weight change while they're riding the elevator? Would they gain mass, or would the gravity of Earth change? No. So whatever their weight is, their weight should stay the same. So as you're drawing your free body diagrams, that vector should be the same all the way through, right? That shouldn't change. So what's changing when you ride an elevator?
The normal force?
The normal force. And in the video you're watching, there's a person standing on a scale, and the scale is what's actually pushing the person up, right? So the scale is providing the normal force. Now, normally when we stand on a scale, we say we're trying to find our weight. But in reality, what we're seeing is the normal force the scale has to provide to support us. Now, as long as we're just standing still and we're not in an elevator, those two things are equal, like both Josiah and Nico mentioned earlier, right? But if the elevator starts to move, now the weight won't change, but the normal force will. So as you're drawing your free body diagrams, you just need to have some normal forces potentially smaller or larger or equal to the weight force, and the weight force won't change. Now, in the directions, it also asks you to come up with the net force, and it also asks you to come up with the acceleration. It also asks you to draw vectors for the velocity and the acceleration. For the velocity, you don't really know the speed, and I'm not asking you to try to use kinematics to calculate or anything. Just use an arrow. Is the velocity upward or downward? That's all we're looking for the velocity. But for the acceleration, it does ask you to calculate it. So you can put an arrow to show, oh, the acceleration is up or down, or you can use a word. If you'd rather just use the word, that's fine. But then also you do need to calculate it. So what do we use to calculate the acceleration?
The net force and the mass of the person.
Good. We're going to use Newton's second law, the net force and the mass of the person. So net force equals mass times acceleration. So acceleration would be net force divided by the mass. How do we figure out the net force on our free body diagrams for those elevator scenarios?
We compare the normal force and the gravity force, and which one's greater or less than.
Good. So we just find the difference between those two forces. There's only two forces, normal and weight. So the difference between them is the net. If they're the same, the net's just zero, right? And if the net is zero, what's the acceleration? Zero. Yeah. If the net force is up, what direction is the acceleration?
Up.
Has to be the same. Net force and acceleration always are in the same direction. Good. So hopefully that helps as you're thinking through those worksheets and trying to complete them. I'm going to try to save you 20, 25, 30 minutes, somewhere between 20 and 30 minutes at the end of the period today to work on that. Now, if you are interacting with students that are in my A-Day classes, they have been given an assignment on Hooke's law. we're going to go ahead and take the notes on Hooke's Law today, but we're not going to do the assignment yet. I'm just going to give you that tomorrow because we meet today and turn around and meet again right away tomorrow. Now, tomorrow's class, I'll probably only need about 5 or at the most 10 minutes just to explain that assignment. And then you'll have the rest of the 45-minute period tomorrow just to work on that Hooke's Law assignment. So if you hear students in A day talking about that assignment, I'm not going to give it to you today. You could always look on Access and work ahead if you want, but I'm not going to explain it today. We'll do that tomorrow. Today, I just want to go over the notes for Hooke's Law. But before we do that, are there any questions about anything we've covered regarding the elevator exercises that are due tomorrow night?
So on the free body diagrams, we don't have to calculate the velocity, just the acceleration.
Yeah, just the
And-
net force and acceleration, not the velocity. That's correct.
Okay.
We're just calculating the direction, right? Because we're not using the weight from the person in the first page, or are we doing that?
Oh, for the acceleration and the net force, you should use the numbers from the first page. So
Oh.
I do want you to actually calculate the net force and acceleration, but for the velocity, just show the direction.
Okay.
Anything else? All right. So as you're working on it later today, it's not due till tomorrow night. So you can also bring questions tomorrow. We have a 45-minute period, and really all I'm going to do is explain the Hooke's Law assignment tomorrow. And so you could also bring some questions tomorrow if you need it, since it's not due till tomorrow night. All right. So here is the agenda for the rest of our class period. Since we're, like I said, we're a little bit off track with the A-day classes. So again, just a reminder, those elevator activities, they're due Wednesday night for you guys. 2 separate assignments. The feelings one is a lab grade. The video analysis is a homework grade. And what we're going to do for the rest of the period today is number 1, we're going to review TOAGAMRB, and we're going to review Hooke's Law, but the worksheet we're going to save till tomorrow. So we're just going to do number 1, and then I'll give you whatever time we have left over just to work on your elevator assignments. So first, can anybody remember what TOAGAMRB stands for? And if you do, type it in the chat. It's an acronym we learned back in the day.
I know the first like 3 letters stand for to obtain is it graphical and mathematical Sonia has it.
Yep. Yeah, so you got us started, and Sonia gave us the last little bit there. Great. So it's been a while. We haven't talked about it. And it's odd, when I stopped to think about what I had planned was that today we would actually start introducing Hooke's Law as a lab. And if we had been on campus first semester, you would have been doing labs all the time, and you would have been using this TOAGAMRB acronym every week. And we haven't used it, but the College Board exam always asks questions about lab. And generally what they ask is, well, it's not really a question, it's more of a directive. They always have at least one question about a lab, and it goes something like this. You have a person doing a thing in a place, right? Generic stuff, could be anything. And then they'll say, okay, you need to figure out a procedure, an experiment that would find a relationship between this and that, all right? And so part A, what kind of equipment would you use from a standard physics laboratory? All right, so that's one they'll generally say. Is they don't give you a list of equipment, they'll just say standard equipment. So you're thinking, you know, scales and springs and rulers and meter sticks and like a movement sensor and a force sensor, things like that. And what I plan to do this semester, regardless of how much we can and can't be on campus, I'm going to start showing you on video some lab setups, because you need to start to learn what some of this equipment is. And I was hoping we would have this whole semester to do that. Now it's looking like that's going to be somewhat limited. And so I'm just going to start, you need to learn it. And so I'm just going to start teaching you, even if we have to do it by videos instead of waiting. But that's the first part. What equipment would you use? The second part then is design an experimental procedure using that equipment to find the relationship between the two things. And then part C, what kind of data would you collect and which pieces of equipment would you use to collect it? And then part D, how would you manipulate, calculate, or graph that data to get a reasonable conclusion? And then part E, if this was the data you collected, how would you graph it? And then draw the graph. And then part F, from the graph, what is meaningful? The slope, the area under the curve, that kind of stuff. Okay, so the whole question will revolve around an experiment you've probably never done and never heard of, because they pick really off the wall things. But they'll be based on principles that you should know, like about force or about motion. And so I want to TOAGAMRB today some practice on Hooke's law. And it is to obtain a graphical and mathematical relationship between. Now, College Board doesn't use the acronym TOAGAMRB. It's actually from a curriculum I use on scientific modeling, and it's not something College Board would recognize, but it's an acronym to help you think, okay, in my lab, my goal is to obtain a graphical and mathematical relationship between. That's what they want you to do. So the acronym guides you into what College Board wants you to discover and wants you to present. And so that's what that's about. Now we're going to take a few minutes, maybe 5-6 minutes, it won't be very long, just to review Hooke's law and what it was. We briefly talked about it last semester, but it's been a while and we didn't spend a ton of time on it. So I want to refocus on what it means. And then I'm going to put you in breakout groups and have you do this. Come up with a procedure. If you were trying to prove Hooke's law in the laboratory, how would you do it? What would you use? What would you measure? What would you graph? How would you obtain a graphical and mathematical relationship between the elements of Hooke's law? So we'll review it first, then we'll put you in groups and have you see if you can come up with a procedure, because that's what you would have to do on the exam. All right, so Hooke's law, what is it? Well, Hooke's law is defining the force of a spring. And where it came up in our notes before Christmas was a very brief introduction to, oh, you know what? Some forces are variable. Not all forces are constant. And a spring force is a variable force. When you stretch a spring, when you first start to stretch it, it's generally fairly easy to start, but the farther you stretch it, the harder it gets. And unless it's wimpy and you actually damage it, you eventually come to a point where you can't stretch it anymore. Or if it's the kind of spring that's designed to compress, you can initially maybe start to compress it, but the more you compress it, the harder it gets, and you eventually get to a point where you can't compress it anymore, unless you have superhuman strength or something. But there's a limit to the amount of force, and the force changes as you compress or stretch the spring. So that's a variable force. It's not constant like some other forces, and so it has its own equation. And that's what Hooke's law tells us. So I'm going to give you just a minute or two to read this through. You've seen something very similar to this before, but I'll let you read it through, jot down in your notes what you need to get, and then I'll make a few comments. So the Hooke's law equation, it's a little different on this slide. You've learned by now in this curriculum, the equations they use in this curriculum aren't necessarily always identical to the equations as they're written on the AP formula list. So there's a slight variation. I don't think the negative sign is on the AP formula list. I don't have it with me today, but I don't think the negative sign is on there. And instead of the whole word spring, I think it just has an S standing for spring, but not the whole word. And I believe that it's the force of the spring is also in absolute value markers, like the X is on this slide. So there's some slight variations, but it's, for all practical purposes, basically the same idea. So you can see here on this slide, it says the K represents the spring constant, and it's measured in newtons per meter. Now the spring constant is pretty similar to something we did spend a fair bit of time talking about, and that is the coefficient of friction. If you remember learning about the coefficient of friction, it was that funny U shape, the mu letter, and it told us how much basically the surfaces would grip each other or stick together, how smooth they would be when two surfaces were sliding and how rough they would be when they're sliding. This is kind of like that, but for springs. Okay, it's a coefficient in a sense of speaking, or a constant that is specifically related to the spring. So if it's the spring in your pen, that's going to have a very small constant, because that's a pretty wimpy spring. If it's a spring on your screen door that pulls the door shut, that's going to be quite a bit stronger than the little tiny spring in your pen. So it's going to have a higher constant, or a larger value for the constant. If it's a spring in the shocks and struts of your truck, then that's going to be even more rigid, even more strong. And so that's going to have an even higher spring constant. So it depends on the design and the function of the spring. And for the spring constant, like the coefficient of friction, you either have to look it up or you have to determine it experimentally. Okay, it's not something you memorize. It's not the same for every spring. It's different for every spring. So you have to look it up or you have to determine it experimentally. Now, the X in the equation represents how much the spring gets compressed or stretched. And the reason it's in absolute values is because we don't really care if we're stretching it or compressing it. The equation works either way. Now, some springs are designed to be compressed, like the springs in a car's suspension, and some are designed to be stretched, like a spring that pulls a gate closed or pulls a door closed. You stretch them out and they pull it back. And so the absolute value is just reminding us we don't really care about the direction. We just need to know how much did it get stretched or compressed. Some springs can do either. You also notice that displacement, that X value, needs to be in meters, because if we're going to multiply it by the spring constant in newtons per meter, the meters need to cancel. And springs, if you can think about how big a meter is, it's basically a little bit bigger than a yard. It's a little more than 3 feet. Most springs won't stretch more than 3 feet, right? Usually the springs are only going to stretch a few inches. And so we don't typically measure it in meters. We usually measure it in centimeters, and you're going to have to convert it to meters so your units cancel. All right, now the negative sign is not even there in some books, and I don't think it's there on the AP formula list, but it's really just a reminder to say all springs exert a restorative force. If you stretch the spring out, it's going to pull back to try to restore its original shape. If you compress a spring in, it's going to push out to try to restore its original shape. Okay, so they always push or pull opposite to the way we push or pull on them. And the whole goal of that push or pull by the spring, that force by the spring, is to restore its relaxed original shape. So any questions about Hooke's law, the formula, or the values, the signs, anything?
So does the negative sign, like if it's not there, then we know that it's not a restorative force?
Well, Hooke's law, if it's there, they're just reminding you that springs always use restorative forces.
Okay.
Sometimes they just ignore it and assume you know that. So
Okay.
if it's there, I usually just ignore it. If you see it in a book and it's there, like I said, I believe on the AP formula list, it's not there. And so I usually don't worry about it.
Okay.
All right. Now, if we think about Hooke's law graphically, because we're TOAGAMRB, we're trying to do the graphical and the mathematical relationship. So graphically speaking, if we put the force that that spring exerts on the y-axis and we put how much it gets stretched or compressed on the x, it should show us a linear relationship. If we look at the equation, nothing is squared, so that shouldn't be quadratic. There's no fractions, so it shouldn't be inverse. It should just be a linear relationship. And again, the negative is more of a reminder of the nature of how springs work than an actual mathematical concern. So we should see something like this. And this is an important graph to consider. Often questions on the AP exam revolve around springs. It isn't always the big experiment question, but this graph and this nature about springs and how the force and the stretching of the spring relate is something that basically every year is going to show up in some form on that exam. So something you definitely want to be very familiar with. And we will not only talk about it today, and then we're going to be doing a lab with it, a simulated lab with it Friday. We'll also come back to it in a couple units down the road. So it's a real key thing. And in fact, some physicists and some physics teachers I've talked to say that basically everything works like a spring. I think that's a little bit of an overstatement, but it is incredible how many different kinds of scenarios you could think about where this equation could help you. So it's definitely one you want to keep in the back of your mind. Now, what would the units be for the slope of this line?
N/meter.
Newtons per meter. Yeah, newtons over meters. Well, what did we just say has units of newtons over meters?
K.
Yeah, the spring constant. So if the spring constant has newtons over meters, what does the slope of this graph tell me? Lucia?
Okay.
Okay, the spring constant. So the area under the curve is not particularly helpful, at least not for anything we've learned yet. That's a little spoiler for future things, but the slope is extremely helpful. Finding the slope would give you the K value for the spring. All right, a couple more slides. We're going to go through these next ones pretty quickly. They're just basically helping you interpret this graph in different ways. So if we had a little bit of force on the spring, it would stretch it a small amount. If we had a large amount of force on the spring, it would stretch it a larger amount. Pretty obvious, but just trying to help you visualize how the amount of force goes hand in hand with how much the spring will stretch or compress. The slope, like we just identified, the slide is just kind of confirming what we just concluded a minute ago. The slope is in newtons per meter, so it actually is the spring constant. And another way you could define the spring constant or explain the spring constant is that it is a number that represents how rigid or how stiff the spring is. Just like the coefficient of friction is a number that represents how rough the surfaces are to each other, the spring constant is a number that represents how stiff the spring is. Okay, so the bigger the number, the stiffer the spring, the harder it would be to change its shape. The smaller the number, the weaker the spring, and the easier it would be to stretch it or compress it. All right, so if we looked at two springs at once, the one with the larger slope has the larger spring constant, and the one with the smaller slope has the smaller spring constant. Okay, since the slope is the spring constant, hopefully that's pretty obvious, but they're really trying to break it down with baby steps here and make sure you're not missing any little detail. All right, so the bigger the slope, bigger the spring constant. So here's your question based on this relationship to make sure you're getting it. You can put your answer in the chat. If this is our graph, the same one we were just looking at, where the blue one is a large spring constant and the green one is a small spring constant, which spring requires the greater force to stretch? So put your answer in the chat, A, B, or C. Blue, green, or is it the same? All right, so it is indeed the blue spring. It is A in our options here. All right, the next question, do a little mental math here using the equation. An ideal spring has a spring constant of 25 newtons per meter. Determine the force required to elongate or displace the spring by 2 meters. So when you got the answer, go ahead and put it in the chat. What force would be required for this scenario? Got a lot of 50s showing up. We've got the spring constant times the displacement. 25 times 2 does give us a 50 Newton force required to stretch that spring. Now, if you think about this, 25 Newtons per meter. So if you apply 25 Newtons of force, it's going to stretch that spring a meter. That must be a pretty wimpy spring, right? Because 25 Newtons is not that much force. And if it's going to stretch it a meter with only that little bit of force, it must be a pretty wimpy spring. All right, next one. An ideal spring requires 3,000 Newtons of force to stretch it, so much more force this time, and it's stretching at 5 meters. What is the spring constant?
It's my keyboard. When I press 6, it automatically come out 66.
Got a happy 6 button, huh?
Yeah.
All right, yeah, it looks like you guys are coming up with the correct answer here. We're calculating K. K would be the force divided by the displacement. So our 3,000 Newtons divided by 5 meters gives us a K value of 600 Newtons per meter. All right, and the last one. A force of 100 Newtons is applied to a spring with a constant of 250 Newtons per meter. What is the resulting displacement or elongation? In other words, how much would it stretch or compress? All right, we're getting a couple of different answers here. I think 0.4 meters has the majority, but we've got a few other answers as well. Let's take a look. We're trying to solve for x. X would be F over K. We've got a force of 100 Newtons. We've got a spring constant of 250 Newtons per meter. So the Newtons cancel, and we would be left with meters since it's 1 over meters. So, and 100 divided by 250 is 0.4. So we should get 0.4 meters. That's how much it would stretch or compress. We don't really know which way they were applying the force. All right, any questions about using Hooke's law mathematically or what it means conceptually? All right, so now we're going to put you in breakout groups and have you come up with a procedure. Let me refresh your memory of what we're trying to get in this procedure here. So we're kind of thinking through the TOAGAMRB acronym. What procedure would help me obtain a graphical and mathematical relationship between, and the two things I want you to figure out a relationship between are in blue font here, the force exerted on a spring and the displacement of the spring. Okay, so those are the between whats, right? To obtain a graphical and mathematical relationship between the force exerted on a spring and the displacement of the spring. So if we were doing a full lab report, this would basically be your purpose statement. TOAGAMRB, the force exerted on a spring and the displacement of the spring. That would be your purpose statement. Okay. So in your groups, I want you to think about, well, what procedure could we do? You may not know everything that's in a physics lab. So just think about the things you know and how could you do it? There's a lot of ways you could do it. I've had 4 or 5 different good procedures come up in the previous classes. So there's not a single way to do it. So don't get too hung up on, oh, what if we're doing it wrong? See what you can think about. How would you figure out the relationship between the force you exert on a spring and its displacement? Some things you want to make sure you include in your explanation. When you come back, everyone in your group should share something about your procedure. Okay. So you want to make sure you cover at some point, what would you be measuring? How would you measure those things that you're measuring? And then what would you do with that data? Like, what would those measurements tell you? And so thinking about your TOAGAMRB, what kind of procedure would help you accomplish this goal, and include at least all three of those things. You can decide in your group how you want to divide up the explanation. You might say, hey, I'll talk about what we measure. You talk about how to measure it. You talk about what to do after that. Or you may say, hey, you talk about the procedure in general. I'll talk about the graphical. And then you talk about the mathematical. You can divide up however you want. Doesn't matter. You can come up with your own system. But you'll have 3 people in a group, and you're basically coming up with a procedure that would accomplish what you see on this screen. Any questions about the goal? All right. I'll go ahead and put you in your groups. Make sure that, yeah, so 2 groups will have 3, 1 group will have 4 people. All right. Off you go. I'll give you about 10 minutes to come up with your ideas. I'll pop around at least once to each group. If you have a question, you need some help, you get stuck, you can hit that ask for help button. Good luck. All right. I believe all the groups are back in the main room now. And let's hear from, before we do, just a quick comment about this. If we had been in campus, anytime we do a lab like this is kind of part of the procedure. I break into groups, you talk about a procedure, and then everybody shares what their ideas are. So you can sometimes perfect your own experiments. One of the things you're always trying to do when you do these in real lab situations is minimize your error. And so sometimes you'll hear another group's presentation and think, oh, well, we still want to do our procedure, but that idea about the way to limit that error is really good, so let's steal that idea. And you basically get ideas from each other and expand your knowledge on different ways to do the experiments. So we can't actually carry it out this time, but let's still hear what you came up with. So group 1, Bob, Hannah, Nico, and Sophia.
So we said for the first part, well, the question was, what do you measure? We said force in newtons and displacement in meters.
Then for the second part, how to measure it, we could use the force gauge, I think it was called, and then you attach the spring to it, and you could put a meter stick along the floor or the table, wherever you're doing it. And then as you pull, at certain intervals, like maybe half a meter, and so on, you would look at what the force reading is and then record both of those.
So after we record the data, we will make a data table and follow the guideline of 10 something. And yeah, sorry. And
Oh, and after you make the data table, you can graph it and find the slope, which would be k, because the entire point of this is to try and find the relationship between the 2 different things.
Good. What would you graph? Like, what would be on your axes to do that?
Oh, you would graph force and displacement.
Good. All right. And then Bob was saying with the data table, there's some kind of little rule that we learned about, something 10 or something like that. So can someone refresh our memory about how we can know we're getting enough data?
The 8 by 10 rule. So you have to have at least 8 points. And then the 10th point has to be, is it like 10 times more than the first point or something like that?
Yeah, good. So 8 by 10 is kind of like TOAGAMRB. It's not a college board thing. It's just a class thing that we do, but it's a little memory device to help you know when you're answering this kind of a question on the college board exam, you want to cover all things about TOAGAMRB to make sure you're completely answering the question. And you also want to use the 8 by 10 rule because a lot of times in the rubric, it'll say the student needs to emphasize that they would gather an abundance of data with a range of values. And so you can just say it that way. We would gather 10 samples of data ranging from this to that. And so that little 8 by 10 is a memory device to help you remember to say, get at least 8 data points and make sure your smallest independent variable value is 1/10 your largest. It could be even greater than that, but you want to have at least a 10 times magnitude of range. Good. Group 2, Greer, Hannah, Lucia. I think you're still muted.
Okay, sorry.
I do it all the time.
Yeah. We're measuring the displacement of the spring based on the different forces that are exerted.
And so the procedure we would do is we would take the spring and attach different masses, masses to it with varying values of mass, I guess. And then you would drop the spring, you would drop the mass, and then you would measure how much the spring stretched from its original place. And then, yeah, you would put that into a table.
And then from the table, you would make a graph and you graph the force on the x-axis and displacement on the y, I think. And then the slope represents the constant, the spring constant. So.
Okay, good. Yeah, you want to flip the axes, but other than that, everything sounds good. That's actually the procedure, pretty much the procedure you'll be doing in the simulation on Friday is exactly what that group suggested, is having your spring hanging, putting different weights on it and seeing how much the amount of weight stretches it. So that procedure is a very common one for this kind of a lab. It isn't the only way to do it, but it is very common. Good. And then group 3, we've got Bella, Josiah, and Sonia.
So number 1 for what we're finding, we're just finding like the distance and the force in meters.
And then we would measure it using a spring scale, and you pull the spring to whichever values in meters that you would like. And then you read the scale part, the spring scale, and it'll tell you how many newtons of the force.
And so now that we have 2 out of the 3 variables that we need for the equation, we could use that to find the different forces and how if you manipulate the elongation, the force is going to change, and the spring scale will tell us that. And then kind of what the other 2 groups were saying is that we could put that into a data table and then transfer that into a graph.
Good. So we have a lot of similarities, obviously, because we're trying to come up with the same results, but slightly different procedures for every group. One group is going to use a force sensor, which I assume would be one of the digital type sensors that I think they said a force gauge or a sensor. So and then stretch it. Another group said they're using a spring scale to measure it and stretch it. And then another group's going to hang weights from it and stretch it. So you're all kind of doing the same sort of thing, but in a different way. And all 3 of those procedures would work very well. They would all give you good results. And ideally, you would come up with a nice linear graph of force on the y and displacement on the x and know the spring constant. And the spring constant is the relationship between the force and the displacement of a spring. All right. So hopefully that helps you kind of start to live out the process that you have to do when you answer those kinds of questions on the AP exam. We'll continue to practice this over and over again this semester with lots of different relationships. And we'll revisit this just briefly on Friday before we start our simulation. And we'll talk about that Friday though. For today, we've got about only 10 minutes left, so not as much time as I'd hoped for you to work. But tomorrow, I'm basically just going to introduce the Hooke's Law assignment and then give you the rest of the class period to work on either one, finishing up the elevator assignments or working on the Hooke's Law assignment. The Hooke's Law assignment won't be due till Friday. The elevator assignments will be due tomorrow night. But all the assignments due at night, not during class. So if you have questions for me, you're welcome to stick around for the last 10 minutes. If you don't, then you can take off and get ready to work on the elevator assignments if you're not done or getting them uploaded. And I'll look forward to seeing you again tomorrow.
All right. Thank you.
You're welcome.
Thank you.
You're welcome.